Thanks a lot. Today I will talk a little bit about, especially about point-of-low power supplies and challenges when using them, especially when using wide bandgap transistors. So today's power supplies are always switching faster. And what do we want? Because what we expect from this, we would like to have smaller form factors and therefore using less resources for producing our power supplies. Here on the slides, you see a little bit of the evolution of power supplies. When you look on the left side, this is a classical power supply, 150 watt, having 6.3 by 4 inch. And here you see it's very nice to mount a wire there with a screwdriver. That's pretty easy. The next slide, we have a state-of-the-art power supply, also with 150 watt. It has 4 times the power density. And when we see already problems, let's say challenges, this is how to connect the power supplies. It's not easy with standard power supply, standard connectors. So you need special tools for this. And here on the right side, I have here now a housing of our current 5 watt power supply. We will see in the future which power we can put in there. So I mentioned that today's wide bandgap devices can switch very fast. I wrote here some numbers from data sheets from GAN and SiC, but also today's silicon transistors are switching very, very fast. So super junction MOSFET with 100 volt per nanoseconds and even IGBTs are switching quite fast. So, but all of these transistor technologies have the same principle. So on the gate, you connect a low voltage to switch a high voltage between drain and source. Sounds very easy. But when you go a little bit more into the detail, you have to deal with the parasitics, like an emitter inductivity. And we all know the induction law, V minus V is inductance L times di to dt. Let's assume we have the IDT from 10 amp per nanosecond, which is possible with gallium nitride transistors, for example. And you have a emitter inductivity of 15 nanohenry, which is only 2.5 centimeter of route on a PCB. You would induce a voltage which is about 150 volt, which is way higher than the maximum ratings of a GaN transistor are. So, and even if you only have a wire through the PCB, this also have an inductivity of roughly about 1.2 nanohenry, you would have also voltage induced here, which is about 12 volt. So when you have only one transistor, you can calculate this pretty easy. If you have 2 legs or 3 legs, it's becoming even more difficult because it depends where you connect your driver ground. Also, I have here 3 possibilities when connecting the driver ground. If you connect the driver ground here in the center, you both transistors are switched like the same. But you have also the layered inductivity add to the emitter inductivity. If you connect it here, you have a different switching behavior than here. And also your transistor what is switching on the left side can influence the switching on the right side. So what helps even for low side applications is to use isolated gate driver and therefore an isolated gate drive power supply. So you eliminate the influence of the other transistor legs. Even better is to use isolated power supply and semiconductors which have a 4 Kelvin source. Then you can eliminate the emitter inductivity and control your switch even more better because you don't have this induced voltage there. A negative output voltage prevents you from unwanted switch on due to the millicapacitance. So this would be then the optimum gate driver, so you can easily control him with conventional technique. Further improvements you only can reach when you also eliminate the inductivities here in the gate loop, and this is only possible then with driver integration to the package. RECOM is also working on this. We have here a project this is called Canon CMOS, where it's a EU-funded project where we work with several European companies and institutes together, where we want to apply wafer-to-wafer bonding. But this is more future, so I don't want to go too deep into this. If you are interested in this, you can look on the webpage or contact me for further information. Today we are talking about isolated gate drivers, or better the power supplies. And also, if you are looking into the isolated gate drivers, you find a lot of information there. So, for example, distance through isolation, which is only several micrometers, creep edge clearances, lots of test voltages, and the common mode transient immunity. But what does all these numbers tell us? Let's talk about common mode transient immunity. Here I have an example. It's an opto-gate driver, and this is therefore a photodiode on the one side, on the primary side, and a phototransistor on the other side. And when you apply now a voltage change between primary and secondary side, you have also current flow through the parasitic capacitances. And if the VDT is too high, the current is high enough that the transistor on the secondary side has a false information. So this maximum common mode transient immunity tells you where the information on the secondary side is this what you have on the primary side. It has nothing to do with reliability. All the test voltages what are given there are well defined and standards, but also all these values are 50, 60 Hertz values or DC values, and nothing have to do with a high DVDT or DIDT. So let's go into the gate transformers. We have a lot of gate drive transformers on the market, but if you're looking for a standard, then you have to look very long because every supplier defining it a little bit differently, and it's pretty confusing sometimes. You have an example of an isolation voltage of 1000 volt RMS. So this is written very on the top of the datasheet, and when you go to the very down, it's small written. The part could be expected to function correctly with several hundred volts. So from this information, I don't get anything out which frequency, which VDT or whatever. So let's see a little bit more in detail gate drive transformers, how they can look like. Here on the right hand, you see a transformer where you only have lacquer wire over lacquer wire winded. So the only isolation is really the lacquer wire. It has the advantage that it can be very small, but you have high parasitic capacitance, and the isolation is maybe not the best. And the middle, you can see almost similar construction, but one side, even primary or secondary, has triple insulated wire, which is better in terms of isolation. But if you really want to have a safe isolation, you have to make a physical separation there. And also to have less capacitance. Good. Gate drive power supplies. We have here similar situation with gate drive transformers. There's nothing standardized, so you have three manufacturers, you have three different values or three different ways how to describe the product. Couple mode transient immunity, the VDT between primary and secondary is mostly missing, and also continuous working voltages are missing. So when we go here, what is related to the gate drive power supplies to the insulation, we have to say higher frequencies will have more stress on the insulation materials. And this also is not always known. Insulation materials major, so they will get worse with the time. So let's look a little bit about the specs about such materials, that you don't have such a picture than on the right hand. So one thing is the breakdown voltage you have to consider on insulation materials. This is given in several kV per millimeters, also only valid when new. It's a 50-60 Hertz value or DC value, also temperature dependent and dependent on thickness. And what is also very important, this is not a median value, or this is not the maximum or minimum value, it's a median value. So you can have some which are even below there. So let's look about this. When you go breakdown voltage versus frequency, so at 50 Hertz they are even high, quite high, but it drops dramatically sometimes, even a factor 10 when you go up with frequency. So especially when you are in the range of several hundred kilohertz or even a megahertz, you have to dramatically drop. What is also very interesting is the thickness of the insulation material has also big influence on the breakdown voltage. And this is therefore that thinner materials can be manufactured without less failures. Therefore, they have a higher breakdown voltage. What else we have to consider when we designing isolation? It's the thermal classes. So in a thermal class, it doesn't say, let's say when you have class F for 155 degrees, that you can use it permanently there. It tells you that after 20,000 hours, this is only 2.3 years, the breakdown voltage is reduced to the half. So, I wrote it in German, okay. So you can see differences in isolation classes when you use class B or class H for the same conditions. You can see class H will survive much more longer the stress. Okay, another effect is the aging through partial discharge. Partial discharge, it's a plasma formation within isolator. And I've tried to explain it here on the picture. If you have here an insulation, which is here brown, and you have a voltage applied on this insulator, there's a voltage across the insulator. It's like a capacitive voltage divider. When in this void, when there is a failure in the insulation, the voltage is higher than the ignition voltage of the plasma, then there will be a plasma ignition. There will be a plasma. It's not a thermal plasma like a welding arc, because you still have insulation, but still there happens chemical reactions. So, and for organic materials, this can lead to carbonization on the surface, and therefore making it conductive. For inorganic materials, it's less sensitive. So, but which voltage is this? So that's not a constant voltage. It's depending on the gas which is in the void, and also the pressure and the distance. This you can see in Paschen curve. So it doesn't mean when you test it on sea level that it also work on the Großglockner Hochalpenstraße. So therefore you have other ignition voltages. And also it's depending on frequency. The good thing is we can measure the voltage. So here I have a setup from a partial discharge testing where CA is your device under test. You have here a high impedance and a decoupling network, and you apply a voltage, and when the voltage on your device under test then drops due to you have a partial discharge, then you can measure the plasma, the corona starting voltage. So a typical test setup looks like this. It's also in German again. So you rise the voltage slowly until your corona starting voltage, you measure partial discharge, and then you apply a defined voltage, have it for a defined time, and then you measure partial discharge. Then you can say something about the condition of your insulation. And when you go down with the voltage, you even can detect when the partial discharge ends. But what does this have to do with reliability? This is a lot of people are working on this, what it really means. I didn't find a lot of literature, to be honest here, what it means when you're above the corona starting voltage. The only thing I found here was this from DuPont. And it mentions here where the corona starting voltage, for example, is here 425 volt. When you apply here a voltage with 1000 volts, you can see after 5 hours it will be damaged. If you are at 600 volt, it's at 40 hours, and the lower the voltage, the longer is your reliability. If you are below the corona starting voltage, you shouldn't have any aging because of partial discharge. But also we have other effects. Dr. Stadler made a very interesting presentation on the wide bandgap user training. He simulated an inductor where you see the parasitic capacitance here. And this is a very nice impedance graph of an inductor. But you also have here a second resonance. And this is due to the interwinding capacitance, which is a much higher resonance frequency then. And he simulated the voltages which are at the beginning and at the end of this winding. And he sees when you switch at the second resonance frequency, the voltage here on the device can be up to 7 times higher than the applied voltage. Another very interesting test was made by Miss Vivian Grau at University of Aachen. They wanted to analyze why in a GaN DC-DC converter the inductor failed. So she made an interesting test. This was she made twisted pair Lacker wire test and built up a H bridge, so that you have a bipolar voltage, square wave voltage. And this is very interesting. She had a standardized hyper test. It survived 5 kV AC. And she applied the 400 volt DC with a slew rate of 14 volt per nanoseconds and 1 times with 107 volt per nanoseconds. With 14 volt per nanoseconds, nothing happened. With 107 volts per nanoseconds, the following happened. I hope you can see this video. This is in real time. Maybe you see here already the corona. And yeah. So let's put it to the next foil. This was done with a switching frequency of 500 kilohertz, 107 volt per nanoseconds, and the isolation was damaged after a few minutes only. we have to say this was only 400 volt, and it survived the standardized BiPoL test with 5 kV AC. So, what has RECOM done for this? Because we also always hear the questions, what can your power supply survive? And as you have seen, as simple the question is, the answer is a little bit more difficult. We developed here a reference design which consists full power stage with isolated gate driver. It's the R-Ref01-HB. You can purchase this at Electronic. And it's a reference design where you can check various transistor technologies, SiC, GaN, IGBTs, MOSFETs, silicon MOSFETs. Doesn't matter. It's isolated gate driver and isolated low side and high side power supply. There are also common power supplies included already. You can use it for TU-247 3-pin and 4-pin power supplies. And here we started our project Barrier Insulation Evaluation Research, short BIR, with Dr. Sommereder of TU Graz and FHU Neum. And what have we done here? We made tests with different voltage stresses. Here on the left side, you see one test setup where we have here our DC-DC power supply, our gate driver, also for the high side, and here the switch, the bridge, with where we apply the voltage with 1000 volt, and the primary side of the DC-DC converter we connected to ground, to the power ground. So on the low side power supply, we have theoretically no voltage stress. On the high side, we are also always changing between primary and secondary side, between plus 1000 volt and 0, plus 1000 volt and 0, and so on. In the center setup, you see we connected the primary ground to plus 1000 volt. So we have on the low side DC-DC converter a permanent voltage stress of 1000 volt constantly. And on the high side, it's always changing from 1000 volt to 0, 1000 volt to 0. And on the right side, we made a center connection so that we have on the low side DC-DC power supply a voltage of 500 volt constant, and the high side is changing from plus 500 volt to minus 500 volt. So we made this test 1,464 hours. We wanted to reach 1,000 hours, but it was in the winter season, so it also took part over the vacation. So test voltage was, as mentioned, 1000 volt with an ambient temperature of 70 degrees. The R12P22005D had about 93 degrees. Limiting factor was the SiC MOSFET we used. Here we didn't want to have a failure because of this, so we kept the temperature about 116 degrees. So therefore the switching frequency was 50 kilohertz, and the DVDT was 65 kV per microseconds, which is already quite fast for such a high voltage. And we performed partial discharge tests on all the power supplies before the test and after the test. And we have seen there was no decrease in partial discharge. It was an increase in partial discharge injection voltage. But this phenomenon is known when it's thermal stable, that the voltage increases. But therefore, that we don't have a decrease, we can say there was no aging due to partial discharge. So we have a little bit more information about this topic. So the complete DVDT advisory report you can download, which was written by Dr. Sommereder. And also we have some white papers for gate drivers of IGBTs, SiC MOSFETs, and GaN gate drivers. So let me summarize. The isolated gate drives have advantages at high switching speed. High switching speed has an influence on insulation characteristics. So the isolation voltages, what are given in the data sheets, are often based on low frequencies. You have to consider this. Partial discharge measurements gives more information about the insulation than high-power testing. And the voltage on the insulation can be higher than the bus voltage. And with our peer test, we have proved that the RECOM DC-DC power supplies are suitable for high switching speeds. And so we have a lot of DC-DC converters for gate drivers, even for IGBT, SiC and GaN, but you can also use them for silicon MOSFETs as well. So we have ranges from 1 to 3 watts. And the RR3 series, which will come up next year, is also an SMD variant. And here we have different isolation versions, which go up to 6.4 kV DC. Okay, thank you very much for your attention. Okay. Do you have any questions? Feel free.
Well, first of all, Markus, thank you so much for your participation, your really interesting presentation on pound of load power supplies in isolated gate driver applications, and also for your flexibility and for jumping in due to our slight technical difficulties. It is a very interesting topic that we actually ask fairly frequently on by customers on trade fairs, exhibition grounds, and also in personal visits. So make sure to stop by the RECOM page and get some of that more information that Markus has been telling you about. So, Axel, what would be the relationship between RECOM and Rutronic?
So we are, as Rutronic, we are working for more than 20 years together with RECOM. We are number 2 distri in the RECOM network. Very successful also in these strange times currently. And very good relationship. And we are happy to have them on board, you know.
Yeah, it's always nice to... Sorry, Markus?
We are also happy to have you on board.
Thank you so much, Markus.
Always nice to hear. Always nice to hear. Us reached 2 technical questions, actually. Will I now read for you, Markus, if
okay.
You are... Okay. Is partial discharge less stressful for the insulation material?
The partial discharge testing is less stressful than high-power testing.
Okay. And how does that compare to the beer testing you've been talking about?
In the beer test, with partial discharge testing, you also test with roughly 50 Hertz, and then you can see how is your insulation at the moment. You can see this, but you don't see the stress of the high switching speed. So we made with the beer test first the partial discharge testing to check the insulation from new parts, and then applied the stress with very high switching speed.
So one part is temperature and one part is the switching stress put on the component.
Of course, yeah.
Okay. Mm-hmm. Then the second question would be, isolated gate drivers or gate transformers. What is recommended selection for a 1 kilowatt to 2 kilowatt 48 volt or 230 volt switched mode power supply? The very long question, I'm sorry.
From 230 volt to 48 volt, I would recommend at least there are P series when you have the switching speeds there. I think they have 5 kV isolation there.
So this would be your choice of component.
At least this.
Okay, and I'm pretty sure that we carry all these components, Axel.
Yes, for sure. This is one of our jobs as a distributor. We have the parts available ex stock. We have the eval boards. As Marcus mentioned, this REF eval board we have available at stock. And so if the customer is interested, for sure, we have it.
So it's best, like when I just saw this presentation and how brilliantly everything was set up, I will give a call to you, Axel, and ask, hey, can I order one of your eval boards? It was an interesting topic. It's interesting.
Yeah. Sure.
Okay,
yeah.
Great. So if that's something for you out there, you're always welcome to contact Axel about more information. And did we get any more questions in? I was told no. So then, thanks again, Marcus and Axel, for your participation. And
thank you so much.
Yeah, we will now switch to a short break session.
Okay, thanks.
Take care, Marcus.
Thank
Bye-bye.
you. Take care.